It tries to solve the problems of passing mutated genes from parents to children. So we call them inherited genetic conditions, and there are more than 6,000 diseases caused by these bad genes. And the idea is that since parents pass these genes through their sperm and eggs, kind of germ cells, so the idea is to catch it at that stage and fix this mutation in sperm and egg, or just an egg, like in mitochondrial genes, because they pass through only mother through the egg. And the children born will be now completely healthy, because the very basic cause of the disease has been fixed even before this child was conceived. So the mitochondrial genes are a little bit different than the rest of the genes, and even though there are only 37 of these genes located in the cytoplasm of the egg, but they cause a great variety of mutations, and that cause the diseases in children. And the idea is that instead of fixing, we could actually replace it with donor mitochondria genes. And this donor mitochondria genes has to come from a healthy egg donor. So in that egg, we just take its cytoplasmic part where the most mitochondria genes are located. And then we basically replace the patient's egg cytoplasm and mitochondria genes with these healthy mitochondria genes. So from now on, this egg will have basically most of its own DNA, which is in the nucleus, will come from a patient from this family, more than 99%. But this 1% of genes will be donor originated from donor egg. And eggs now could be fertilized using very basic in vitro fertilization techniques, and then early embryo transplanted back into patient. And the idea is from now on, this family will have healthy children because these mutated genes have been corrected. Of course, before going into human eggs, we did lots of work with animal models, and we used non-human primates, rhesus macaques specifically, and showed 3 years ago that this procedure can be done pretty effectively, and we showed that by birth of healthy infants. The 4 infants were born in 2009, and we published that time in the Journal of Nature. So it took us about 3 years actually to translate it to human, at least to the egg and early embryo stage, which is considered pretty fast pace. The straightforward application, of course, of this technology to families that are affected by this, the mutations. Unfortunately, we only can find out about it once the family already has a first child with this disease. And so this therapy would be available to them. So if they want to have another child, in this case, of course, healthy, then this technique should allow them to have biologically their own children minus these mutations.